And we're going to talk about a very special kind of momentum, and that's rotational momentum. Bicycle wheel, and let's see what happens when we hang this bicycle wheel from these strings. I'm going to spin it very fast, like that, and it'll just sit there and spin and spin and spin. Now I'm going to cut or burn one of the strings. And it will keep on doing that, it will not fall over. So what's happening there? And that's what this is going to be all about. So this is all about momentum. And we have two kinds of momentum. If you imagine a curling stone going down the ice, it goes in a straight line, and it has velocity and mass. And this velocity and mass is momentum, linear momentum. We also can take a curling stone and spin it, looking at it from the top. There's a handle, looking from the top, and it spins like that. And that's called rotational momentum. And instead of being mv, it is I omega. I is the moment of inertia. It's like mass, it's how hard it is to turn something. And omega is how fast it's spinning. And it's like velocity. So these are actually the same kind of thing. This is mass times velocity. This is moment of inertia times rotation. And so let's take a look at some of the, but we're going to look mostly at this one. So what we have here is, again, the bicycle wheel. So I'm going to turn. Okay.
Yeah, it's okay.
What we have here is the bicycle wheel, and I'm going to stand on a platform that rotates like that. Spin the bicycle wheel. Let's see, it's spinning in this direction. And by the way, because it's a vector, we have to assign a vector value to it. And we do this by curling our hand, our right hand in this direction. The thumb points, our fingers curl in the direction of the wheel. And so this one's spinning that way. So, and my thumb points in the direction of the vector. If I flip this upside down, I'm going to change the angular momentum. Let's see what that does to me. I'm going to stop it again and spin it. There we go. And so I'm going to turn it, and I start to spin. Now look very carefully at the direction that I'm spinning. When you turn a spinning wheel upside down, look, it's spinning in this direction now. When I turn it upside down, it's spinning in the opposite direction. You get that? Spinning this way, and when it's upside down, it's spinning this way, the other way. That means the angular momentum is not the same. So how does this conserve angular momentum? Well, watch. The wheel is spinning this way. When I go like that, I spin the other way. So the total angular momentum stays the same because I have absorbed some of the angular momentum of the wheel. Another way of looking at this I'm going to stand on this rotating platform, and I'm going to try to change my moment of inertia and see what that does to my angular velocity. So I have two weights, one on each hand, and when I move these weights in, my moment of inertia becomes less. When I take the weights out, my moment of inertia becomes more. But if we look here, the angular momentum means that the product of inertia and angular velocity must stay the same. So if I make I less than omega, the angular velocity must be more, and vice versa. So let's see what happens here. So stand on this platform, start to rotate slowly, and then I will reduce my moment of inertia. And of course I speed up. And when I take it out, I slow down again. And speed up, and slow down. So what is happening is that the angular momentum there is being conserved. And so you can have a lot of fun with spinning things, and there's an awful lot more to this. And I hope you'll take time to have a look at that, maybe research this.